this is the problem that we are presented with. And so if you're thinking about like a semester test kind of question, this question looks something like, plant personnel have measured the power generated and the amount of fuel being consumed by a particular machine on site. They have produced the following table with data and perhaps the following graphic showing the data points plotted. Find the relationship between the fuel flow rate and the power generated. Assume that this relationship takes the form of AX plus B. There's an obvious way to solve this problem, especially within the environment that I have open here, right? I've got my Excel, I've plotted the data points. I think most of you will be familiar enough with Excel to select add trend line and then select from the selection of curves. But I hope that after this lecture you will be more able to answer some conceptual questions about why this list is as limited as it is. You may very well ask, why is there no free-form entry field here where I can just supply the functional form that I'm interested in? For instance, I often would like to fit perhaps a first-order step response of the form 1 minus e to the at, right? Why can I not just type 1 minus e to the at and Excel can find out what a is? Why is that not an option on this list? And the answer is hidden within the mechanics of linear regression, and it's hidden in that word, linear. Linear equations occupy a special position in mathematics. Sets of linear equations have single, well-defined solutions and very easy ways of checking whether that solution will in fact exist. So the preconditions for an existence of a solution, linear equations, are easy, straightforward. You've known about the determinant for a while. So you know that if I calculate the determinant and the determinant is non-zero, then I will have a nice, distinct, unique solution to a set of linear equations. Solving the parameters for linear regression involves solving a set of linear equations. So that's the key idea, right? And I'm going to walk you through the kind of formulas behind that in Python now. But suffice it to say that the thing that all of these relationships have in common is that they are all of a form which is called linear in the coefficients. So when we talk about linear regression, we are doing linear regression, or Excel is doing linear regression in all of these cases. So whether I choose exponential, linear, logarithmic, polynomial, power, everything except this last one, the moving average. All of these all of these radio buttons activate a linear regression routine. This may be surprising, especially if you have imagined that linear regression is about straight lines. The linear part of linear regression doesn't have to do with straight lines. It has to do with the shape of the equations that we're fitting, specifically how the coefficients appear in those equations. So all of these are either in a form that is already linear in the coefficients, like for instance the polynomials, I'll show you that now, and the others, the exponential, the logarithmic, and the power law, can be made to be linear in the coefficients by doing transforms, specifically by drawing logarithms, or in the case of the logarithmic fit, raising exponent. And so you can produce an equation which is linear in the equations from all of these forms, which is why they are here. Because linear regression, now when you're doing it through the Excel interface, right, you've got this kind of limited palette. You can select one of these things and you can select the order of the polynomial, but the reason why only these options is available is because these are all linear regressions. And there is no built-in nonlinear regression routine in Excel. But of course, we can kind of work backwards and build our own. So let's just go to a little bit of background about the theory here, because I'm going to show you just simply how to solve this. It shouldn't surprise many people, but you could just do this, right? This is a perfectly reasonable solution to the original question as worded. In other words, if the question was, here is some data, fit a straight line to it, right? A perfectly reasonable way to proceed is to open up Excel, type in the data points, do the graphics, right-click, there you go. Now, while I'm in Excel, I just want to also mention that I've seen far too many people rely on the formula being displayed over here, and then they'll perhaps retype these. I just want to also clue you in that there are two special functions in Excel that are very useful in this regard, called slope and intercept. And so you can basically say slope, and you supply, confusingly, you supply the y's before the x's. But you select the y's, and then you select the x's. And that'll actually give you just that one slope coefficient, while intercept will give you the intercept part. And so you shouldn't rely, it's maybe useful to display the equation over there, but definitely if you're using this in downstream calculations in your spreadsheet, you should be actually using the slope and intercept formulas. So, okay, now let's do a little bit more math. So if we were doing the same problem in Python, and why would I do this? Why would I ever be unsatisfied with the options that Excel provides us? Excel is limited in that palette of options, right? So there's one problem. Another problem, which is not as immediately clear, is that Excel is limited in its evaluation of the fitted polynomial in a very specific way. It doesn't actually allow you to draw the polynomial as the exact polynomial that you have fitted. Let me try and repeat that in a way that is not so obscure. So I want you to observe what happens when I fit higher order polynomials here. So let's ramp up the polynomials. Now I'll show you in Python in a second, but the true polynomial which actually goes through these points deviates quite significantly from that straight line. The problem is that Excel is evaluating that polynomial only at the data points, and then drawing some kind of like a best smoothing line through those points, which means that the curve that you see is in fact not the polynomial that you think you see. And there is no immediately easy way of obtaining that. The only way that you would be able to do this, but you would have to build a whole extra set of x's that are more closely spaced. Then you would need to build a whole column that includes all of the points evaluated at all of those points, and then you would have to plot those points. As a general rule, you should never use smooth curves in Excel, because that smooth curve view really doesn't actually match any of the math that you think it does. It's really a completely different fit. So it's a very misleading view, and I'll show you in the Python section now. But so in other words, this allows you to imagine that that sixth order polynomial fit actually resembles a straight line between the points, when in fact it doesn't. So if we now go to the linear regression, that's the first thing, is I want to be able to see more closely spaced points, and Excel makes that quite hard. And know that polynomial regression curve is not actually the polynomial that you think it is. It is a smooth curve fitted through the points, through the function evaluated only at the x points that you used, right? So it's not actually showing you the shape of the polynomial that you're fitting. Furthermore, you are restricted in the number and kinds of functions that you can fit. You only have those options, where if you actually have a different, option in mind, you can't actually do that. Okay, so I'm just going to use pandas here to read the exact same Excel file that we had open just a second ago, read the same data. Right, so I'm just going to go and have x and y from the fuel flow rate and power generated. And if we scatter that, we can see we've read successfully. Now, I'm going to do a little bit of mathematical preamble here, just so that you understand why the matrices that we're going to use look the way that they do. So now this should be familiar to you from BSS, but perhaps I believe they haven't actually posed it. They may have just posed it in terms of writing down the normal equations just here is how you do it. This is a more general form. Now, this you can just follow along in the textbook as well, so it's not meant to be completely exhaustive. There's a lot more in the textbook, but this does show you the basic idea. If we're trying to fit this equation, so we have an equation y is equal to ax plus b. That was the equation that the problem gave us, right? Fit this line, figure out what is a and b. A very important kind of mind shift that you need to make in regression is you need to reverse what you think you know about the knowns and the unknowns. So normally you would look at a line like that, and you would imagine that in most applications, you would know a, b, and x, and your job would be to figure out y, right? That's the calculation direction. But in this case, we have measurements of y and x, and our job is to figure out a and b. In other words, a and b are the unknowns in the problem, and x and y are knowns. So if we're doing regression, x and y are known, but a and b, or all of the parameters, are unknown. Another thing that is important to understand is that when we're doing regression, we are effectively always going to say we have as many copies of the equation that we're trying to fit as we have data points. If you think about doing this in Excel, it becomes quite obvious that you would have to drag that formula down and have one of those. So you'd have a version of that exact same formula, but you would have 10 of them in the case of 10 data points, right? So I've just copied that down just here mathematically. But basically you can see the a's and the b's are the same for every version of that equation that I've written down, but the x's and y's are changing. So there's a different x and y, it's the one that we observed, for every one of these data points. But there is the same a and b for every one of these times that I wrote the equation down. And if you think about regression, what we're really trying to figure out is we're trying to find a and b that will make all of these equations true or equal to one another. Right? Because we're trying to find, in the best case, if we have exactly the right formula, we will go exactly through the data points, and effectively we just are asking, what should a and b be so that all of these equations hold? Now, I'm going to make it harder by making it easier for me. I'm making it harder for you because I'm going to use matrix notation. It is almost impossible to attack the regression problem in any scale without reposing it as a matrix vector problem. The very, very simple case of first order polynomial is well studied, and you can look up the formulae for the coefficients in your BSS textbook. But I'm going to show you that you don't need those formulas basically ever. In fact, you should never use them, is my positive affirmation, because they are numerically not well behaved. So you should never use those normal equations that you have in your book. Definitely not for many data points. Really avoid it. Okay. This form of that, now I want you to see that these are exactly the same equations, right? I've just written that out as a vector matrix equation. So I now have this vector of y's, which is all the left-hand sides of those equations. And I have separated out the coefficients into a vector. So I have this coefficient vector, which is the vector AB. And I have this matrix over here, which are now the coefficients of this equation. You see, it's a bit confusing, right? Because we have only a few words. So there are two ways in which I'm using coefficients here, right? There are the coefficients in the matrix equation. And recall there that the x's are known, but the a's and the b's are unknown. And so in terms of this is a constant matrix. This is a constant matrix. And this is the unknown. So if I recast that as a matrix equation, I effectively have y is equal to x times b, and you can now say my job is to figure out b, or beta, right? Now, there is a problem. If you refer back to your linear algebra, the first thing you learned about solving matrix equations is that you cannot solve the matrix equations if the coefficient matrix is not squared. In fact, you can't even calculate the determinant of a matrix that isn't squared. Remember, your instinct should be something like, oh, I will simply multiply from the left by the inverse of x. Right? If you were solving this as a normal matrix equation, that's what you would do. Except in this case, obviously, the inverse of x does not exist. It's not like it's a weird number. It just straight up doesn't exist because non-square matrices do not have inverses. They do not have the thing called an inverse, right? And so another way of thinking about these equations is to say, right, this is effectively an overspecified set of equations. And we all know that an overspecified set of equations in general has no solution. Remember, underspecified, you have infinitely many solutions. Overspecified, you have no solutions. There's no set of A and B, obviously except in this particular case that they call the degenerate case, where all of the data points are exactly on the straight line. And there I could actually satisfy that equation. I could actually get the left-hand side to be, because obviously if I just knew A and B, if I said, okay, I'm going to generate lots of x's and y's with A is equal to 1 and B is equal to 1, they will all satisfy this relationship. But the general case is that they don't, and therefore if I subtract the left-hand side from the right-hand side, I actually end up with a formulation known as the residual formulation. And so I can't solve these equations exactly. Why? Because the equations are overspecified. Another way of seeing this is that the X matrix is taller than it is wide. It has more, there are more equations than unknowns, right? So the problem is overspecified, and I cannot solve it exactly. And now I need to negotiate. So now it's like mathematical negotiation. It's like, so, okay, I can't solve it exactly. I can't get that to be 0. But how close to 0 can I get? And what does that even mean? Like, how do I measure closeness to 0? And the way that people have settled on is that we will express this equation in residual form. So in other words, we'll subtract the left-hand side from the right-hand side, and we will say that there's an error made at every equation. And we will call that the residual vector. And then we will attempt to make the length of the residual vector as small as possible. And you'll be, if you look at this formula over here, this formula is the Euclidean distance formula, right? So it's, we take all the elements of the error, we square them, we sum them all together, and then we take the square root. So in the two-dimensional case, this is Pythagoras. In the larger dimensional case, I think all of you have come across the Euclidean distance in higher dimensional spaces when you did vector math. So effectively, that's what we're trying to do. An important property of the square root function is that it is a monotonic function. And we'll be exploiting that. So monotonic just means that it always goes up, right? It starts at 0 and then goes up all the time. And so we'll be exploiting that by saying any minimum that we can find for the square root of that sum of squares is going to be the same. It's going to be the same to minimize just the sum of squares. And in most cases, we will therefore focus on minimizing just this little part inside, which is known as the sum of squares, or the sum of the square errors. And I've used this notation here. Is everybody kind of familiar with that notation for norms? So that's the kind of the length of a vector, right? So it's these bars that indicate that it's a norm. So effectively what you can see, you'll see references to this if you kind of search for linear regression. It's the square of the norm, but effectively it's just the sum of the squares. Okay? And so this is what we set ourselves to minimize. I'm not going to go through the proof, but I just want to prime your intuition by imagining that if I have linear equations, if I have this kind of equation over here, lots of linear equations, right? And I square them, I'll end up with equations that have squares in them, squares of A and B, up to squares of A and B, right? And if I were trying to minimize that, like you guys understand how to minimize things, I would take the derivative of that equation. which means I'll end up with linear equations. So if I try to minimize a set of equations, I take the derivative and I set it equal to 0. In this particular case, the derivative of these squared equations will be linear equations. And that's the magic of linear regression. Because we're taking the square of the error, we're then taking the derivative of those square errors, and those derivatives are linear in the parameters. Because of that, there is an analytic solution which you should never use. You should never use this, but it is a thing that exists. There is an analytic solution which is called the Pseudo Inverse solution, and this is the one that's in the textbook. Now, there's little, so that's the formula. So you'll come across this. This is known as the Pseudo Inverse because effectively it's the thing that we would have liked to multiply with. This thing over here. Remember, we had this equation over here, which was y is equal to x times beta. And I said, wouldn't it have been nice to multiply by the inverse of x there in order to get the beta? But then we hit a snag because the inverse of x doesn't exist because x isn't squared. And so it turns out when you solve the equations, as I just mentioned, by taking the square of the errors, taking the derivative and setting them equal to 0, you end up with this analytic solution. And this element over here is now known as the pseudo inverse because of this, because it translates the formula into this form. And you can do this. The nice thing about the pseudo inverse solution is that it is easy to do. In other words, you can write code easily that does this. And strangely, in a modern time, it's going to look harder for you because NumPy and SciPy exist. But if you were using a very dumb programming language like C or Fortran, right, this would be easier to implement, which is why it's still in your textbook. However, it is numerically unstable, and so you shouldn't use it. I just want to show you that it does, in fact, work. So there's some NumPy preliminaries here. I've tried to be a little bit more explicit about how that works in the notebook, but basically I'm forming that Y matrix over here by just casting up the, it's maybe a little bit hard to see, but that's a lowercase y and that's an uppercase y. That's an uppercase x and a lowercase x over here. This numpy.c underscore is a kind of a utility that is supplied that is there for creating column matrices. So because you have these NumPy arrays, they're one-dimensional, but I actually want like a matrix, I can just use this notation and that will make me a column, a two-dimensional thing. In other words, stack that thing into the column. And then I'm just adding ones. Now you see what I'm doing. That's the big Y, and now I've got my big X, which is really just the X's and ones stacked next to one another. So this BMAT, that B stands for block. So I'm making a block matrix from those two matrices. I'm stacking them next to one another. Right, and I then just type over this formula from the textbook over here. I quite like the way that works out because using these NumPy matrices, they have these properties. So there's a transpose property, there's an inverse property. And so you can kind of implement this almost exactly the way that it looks on paper. So you just kind of write it just the way that it looks, and it works. Side note, like the NumPy guys actually don't like matrices. So they would like you to use arrays wherever possible. Matrices also have this .a property, which is basically that matrix but in array form. And so if we use that, and I'm going to carry on with x and y as arrays from now on, you'd have to write it like this, which is not exactly as satisfying. I'm led to believe that you have come across this @ operator before. That's the matrix multiplication operator in Python. It's a Python operator. Weirdly, it's a Python operator, but it's only actually implemented in NumPy. So like if you don't have NumPy, it just doesn't work. But it is the dedicated matrix multiplication operator. Right, so this is the textbook version, which I've mentioned that you shouldn't use. So you shouldn't do this. You should be using dedicated solvers to solve this kind of problem. And the problem that we're going to be, or the solution that we're going to be using is this linl.least square. So that LSTSQ is chosen like it's a programmer thing. Programmers hate vowels. So, you know, like they've just taken out all the vowels to make it easy to type, but then it is kind of proportionately harder to read. But that's supposed to be least squares, and we're solving a least squares problem. It's expecting the two matrices that we've already formed as arrays. I think it may work with matrices as well, but it's kind of, with NumPy stuff, it's always best to imagine that it doesn't support matrices. Often weird things happen. So it will then calculate beta, but it also calculates the residuals, which hopefully you now know what that means. So that's the difference between the left-hand side and the right-hand side for each one of the versions of these equations. And the rank of the X matrix. So everybody who knows what the rank of a matrix is? The rank of a matrix is the number of independent rows. So in other words, if there are two rows that are just multiples of one another, or maybe duplicated rows, in those cases, when that happens, that's kind of when the other formulas start failing, is when you have like duplicated rows, because now you have like you have a determinant that is even more poorly conditioned. So it wants you to know what the rank is, and I can't remember what that is. I have seen that some people have still not learned this. If I press Shift-Tab while I'm inside a parenthesis of a function, I'll get this handy little help. If I keep holding down Shift and press Tab again, I'll get the full docstring. So it'll tell me here what exactly is S. So it says, okay, here are the returns. It returns the residuals, the rank, and the singular values of A. We'll get to the singular values in later lectures. I'll actually teach you what they are, but not now. Okay, so that's the one that you should be using if you have an interesting linear regression problem. So specifically, if you have a linear regression problem that is not a polynomial. Because if you have a polynomial, there are a whole host of functions built into NumPy that are specifically built to do stuff with polynomials, right? So here you can see, add two polynomials, take the derivative of a polynomial, fit a polynomial. That's the one we need, right? And so we can use polyfit, and you can see that this is now significantly easier, right? So now we just pass the raw X data and the raw Y data and specify an order for the fit. And so if I wanted a sixth order polynomial, I could just specify 6 in that last parameter over there. So this is the one that you should be using to fit polynomials. There's literally no reason why you should ever use anything else. If you are in the NumPy environment, if you are fitting general case polynomials, in other words, just a polynomial, that's what you want to fit, right? You will use polyfit. It is a mistake to use anything else. Right, so as I mentioned, there are issues. Let me just run this again. Sorry, I've got some bad data here. So as I mentioned, there are issues when we evaluate these fits between the data points. And what you really should be doing is what I've done over here, where I've created lots and lots of X points. So I've just generated, in this case, 100 of them. But of course, you know, we could be just go crazy and generate 1,000 of them. Okay, so I'm generating many points along this straight line, and I'm just drawing the points, and I'm drawing the linear regression. Now, actually, sorry, I'm going to mess with my example here. I'm just going to choose this again. Okay, so I'm going to do this with a small number of points, and I'm going to do this with many points. Okay, so the one line here is covering the other. There's a blue line and an orange line. You can't see the blue line because they lie on top of one another. And so obviously for a straight line, there's not much utility in resampling. If you can draw a line between 2 points, it's going to be a straight line anyway. It becomes problematic when we use higher order fits. And you can see the problem over here. I've now done effectively, this is the version, the orange line is the version effectively that Excel would show you, right? It's the line that connects the fit evaluated at the x coordinates where the points were, right? The blue line is the actual polynomial evaluated with a much more closely spaced grid. And you can see here that we would have completely missed that if we hadn't sampled more closely, right? And so this becomes more and more important the more curvy your functions are, right? So if your functions are quite straight, you're not making that big of an error by approximating them by straight lines, right? But if they are quite curvy, you may be making quite a big error by approximating them with too far apart spaced points. Right, so this is the recommended method that I recommend that you use. You can see polyfit is super powerful. It works. Now, why did I ever show you the other methods? Polyfit specifically only works for polynomial functions. If I have one of these other functions, like a log or an exponential or some other function which can be translated to linear functions, I will need to form my, I may need to form my equations myself. There's another option which is also not available in polyfit, which is, what if I want to do this exact same problem, but I want to do it without, I want to set b equal to 0. In other words, another way of posing that problem is I want to force the intercept to be some number that I want, instead of just whatever I have over here. In this case, I would need to form my matrix specially, because polyfit doesn't allow that option. It doesn't have an option to say force the intercept. So if you have weird functions, weird functional shapes that aren't polynomials, or if you have special requirements which lead to matrices that aren't the matrices that like are the standard ones, which has a row of ones over there, you can't use polyfit. So you should try to use polyfit if you can. If you can't use polyfit, you should use the least squares solver. But you should never use the normal equations, and you should never use the pseudo inverse. Right. When I say never, if you have any kind of alternative, sometimes you're just stuck and you have to solve the problem in a maybe like a low-level language or something like that. Practically, I can't think of a good reason why any of the people sitting here would ever have to do that like in their job. Okay, so is everybody clear on linear regression? Okay, so not quite done. Still have some minutes left. So I keep saying linear regression, but what about nonlinear regression? So if we understand linear regression, and if we understand the core of linear regression being minimizing the sum of the square errors, we can actually say, but wait a minute, can't I just minimize the sum of the square errors and just do it numerically instead of doing it analytically? So linear regression has this wonderful property that there's an analytic solution. Okay, so people use it because it's easy and quick and very reliable. Nonlinear regression, I used to just say this, but I've actually found like a really good example. You should always try linear regression. You should try hard to do your problem using linear regression instead of nonlinear regression. And the reason why I say this is because your temptation is going to be like, once I show you how curve fit works, there's going to be quite a strong temptation to say, I see what you mean. Curve fit can solve linear problems and nonlinear problems. Therefore, I only need to know the one tool. Thank you very much. I will never use linear regression because I will always use, it's always easier to use a more powerful tool and remember less. And hopefully I'm going to show you that you shouldn't do that. Okay, so nonlinear regression is implemented in scipy.optimize.curvefit. And here is how it works. You define a function, which is the function that you are trying to fit. The first argument of that function is the x value of the data that you're trying to fit, and all the remaining arguments are fittable parameters. So you can just say A, B, C, D. You don't have to call them A and B. You can call them gamma or whatever it is in your actual formula that you're trying to fit. And you just put them all in there. You write the function so that it returns the y of the function that you're trying to fit. And you then call scipy.optimize.curvefit. You give it the function, you give it the data, and you give it an initial guess. Now, here's already like the first little alarm bell here is like I didn't need an initial guess before, right? Before I just said, give me A and B, and I solved for it. Here it's like, what do you think A and B maybe is? Maybe just so that I can get a start. This is going to be quite important in a couple of minutes. So, okay, it is able, and if you've been paying attention, you'll recognize those exact same numbers. We've seen exactly the same numbers every time we run this example, right? So we just get the same numbers all the time. So it's 1.859 and 0.08, say, okay? And that works fine. So, okay, job done. Curve fit. Just use curve fit, write the equation that you want. You don't have to worry about matrices, you don't have to worry about anything else. Okay, but let's build a data set. A range is kind of the NumPy version of range. So just like generating points from 1 to 10, 1 to 9. Here's my equation. 2 times sine of 3x plus x plus 1. Okay, so that's obviously nonlinear. It's nice because it's transcendental, so it combines sines of x's and things and x's that aren't sine, right? So you wouldn't be able to do one transform and get like a linear version of that. So I build the data. So I now know my parameters are 2, 3, 1, 1. Okay, that's the correct answer. I haven't added noise. I haven't done weird things with measurements. Just done it. Okay, here's the version of this that we do with scipy.optimize. So I've defined my fitting function just the same way as before. I'm going to do this a couple of times. So I just define a function that does the fitting and does the plotting. So I can just call it again. So I give it an initial guess. And there you go. Success. What is wrong with this picture? We expected the lines and the dots to be on top of one another. Am I right? We generated the data, right? Why can't it find the right parameters? I gave it some kind of it's pretty close, right? So remember the correct answer is 2, 3, 1, 1. I started with 1, 1, 1, 1. And spectacular fail. Okay? Now, the problem is we weren't close enough to the right solution. If we start closer, so if we start there you go. Perfect. No problem. Right? So it's not like I did something wrong. Right? In fact, if I start close enough but just not exactly on it, I still get close to the right answer. If I get close enough, I need to start pretty close. There you go. Okay. So if I start at 2.9, it'll round that up to 3 for me. Okay? Awesome. So this is a problem. But you may say, and I've summarized the problems here in this table. If you're watching this on the video, you can just pause and read this, right? But if we start at a different point, we'll get a better solution, right? So this beta 2, we get a better solution. And now you may think, okay, at least I'll know when I've got it, right? Because if the curve is right on the points, the error will be 0, and I'll know that I have the right answer. Turns out, not so much, because look at this, right? I can calculate the fit error for beta 2, right, which is 0, just like we expect. But this also has a fit error of 0. Right? That curve goes through all exactly the same points. And if I have convinced you of one thing, I hope that I've convinced you now of one specific thing. Many of you use error as a proxy for correctness. In other words, they say, well, the line went through the points, so the equation must be right. I'm here to tell you this is unfortunately not true. There are unfortunately an infinite number of equations that go through any number of points. So getting your equation to go through the points is no confirmation that you've got the right equation. Not at all. And the problem of nonlinear regression, in other words, fitting nonlinear equations to data points, is fraught with this problem. Look at what has happened. I've shown you 3 examples. I've shown you with known parameters. We generated the data. We could see with our eyes what the formula was, right? That if we didn't start pretty close to that exact answer, we didn't actually get back that exact answer. Even worse, if we started sufficiently far away, so we couldn't even rely on the fact that the fit was bad to tell us, to alert us that we've got the wrong parameters. But because if we started around 9, we would get 0 error just as good as when we started close to 3. So, the big lesson of this is linear regression is amazing. Right? You pay only a very small price for a huge amount of benefits. And in fact, the allure of like a general purpose fitting tool is it's like fake glamour, right? It's a siren song. It looks very powerful, it looks like it's going to solve all your problems, but it doesn't. So you should try linear regression before you try nonlinear regression. You should be trying nonlinear regression kind of as a last resort.